Faster-than-light travel is forbidden for anything pushing through normal space, yet Einstein's general relativity still leaves a narrow opening. Space-time can expand, contract, and carry distances with it. That fact is unsettling, because it hints the limit may police motion inside space, not the motion of space itself. Light in vacuum moves at 299,792 kilometers per second, and that number sets every clock, radar pulse, and navigation signal we trust. Tonight, we'll treat warp drive as testable logic from scratch, the Alcubierre metric, the idea of a warp bubble, and the hard constraints set by photons, curvature, and energy. You'll see why negative energy keeps appearing, why causality becomes fragile, and what modern papers try to fix. Thank you for giving me your attention. And now, Part 1. What is warp drive, and why does physics even allow it? The most unsettling fact about faster-than-light travel is not that it seems impossible, but that the equations describing our universe never fully closed the door. According to every laboratory experiment ever performed, nothing carrying mass or information can outrun light through space. Particle accelerators at CERN confirm it. Atomic clocks aboard GPS satellites depend on it. Laser-ranging experiments across millions of kilometers agree to extraordinary precision. And yet, when Albert Einstein completed general relativity in 1915, the theory quietly allowed spacetime itself to behave in ways that motion alone never could. This tension sits at the heart of warp drive. It does not begin with engines, spacecraft, or speculative technology. It begins with geometry. In general relativity, gravity is not a force pulling objects through space. It is the curvature of spacetime itself. Mass and energy tell spacetime how to bend, and spacetime tells matter how to move. That statement, now confirmed repeatedly by observation, changed how physicists think about motion at the deepest level. When NASA detected gravitational waves in 2015 using LIGO, those signals were not objects traveling faster than light. They were ripples in spacetime itself, stretching and compressing distances as they passed Earth. No law was broken, yet space changed shape faster than any spacecraft ever could. The key detail is subtle and easy to miss. The speed limit applies to objects moving within spacetime, not to spacetime as a structure. During cosmic inflation, a phase supported by measurements of the cosmic microwave background from NASA's WMAP and ESA's Planck mission, regions of space expanded away from each other at an effective rate far exceeding the speed of light. Galaxies were not racing through space faster than light. The space between them was growing. General relativity allows this because no information was locally transmitted faster than light. Each region remained consistent with relativistic rules in its own neighborhood. That distinction is where warp drive first appears not as a loophole, but as a direct consequence of how Einstein's equations work. In 1994, Mexican physicist Miguel Alcubierre published a short paper that startled the theoretical physics community. Without invoking new laws or speculative particles, he showed that Einstein's equations permit a solution in which spacetime contracts in front of a region and expands behind it. Inside that region, a spacecraft could remain locally at rest, never exceeding the speed of light relative to its immediate surroundings. From the outside, however, the distance between departure and arrival could shrink dramatically. The ship would not outrun light. The path itself would change length. Alcubierre described it cautiously, emphasizing that the solution was mathematical, not a blueprint. Still, the idea was precise. The equations required a warp bubble of spacetime, moving through the universe while the contents inside experienced no extreme acceleration. From the crew's perspective, clocks would tick normally. Instruments would behave as expected. No relativistic mass increase would occur. This was not science fiction propulsion. It was spacetime engineering. Physicists paid attention because the solution respected local causality, at least on paper. Inside the bubble, no physical signal violated the light limit. The ship simply occupied a region where distances were reshaped. Alcubierre himself wrote, "The warp-drive spacetime can be constructed within the framework of general relativity without introducing new physical principles." That sentence has echoed through decades of debate. History provides an important parallel. When Einstein first predicted gravitational waves in 1916, many physicists doubted they were real. For decades, they were treated as mathematical artifacts. It was not until the 1970s that indirect evidence emerged from binary pulsars, and not until 2015 that direct detection settled the matter. Warp drive occupies a similar position today, permitted by equations, unsupported by evidence, and constrained by conditions that may never be physically realized. One of those conditions appears immediately. To shape space-time this dramatically, the equations demand regions of negative energy density, not low energy negative. In everyday physics, energy is always positive. Mass adds energy. Radiation adds energy. Even empty space contains vacuum energy, measured through quantum field effects. Negative energy sounds fictional, but it is not entirely absent from physics. In quantum theory, the Casimir effect demonstrates small regions where the energy density drops below the surrounding vacuum level. This has been measured in laboratories using closely spaced metal plates with forces consistent across experiments. NASA has referenced these effects in studies of quantum vacuum behavior. However, the magnitude involved is tiny, far beyond anything capable of shaping spacetime on macroscopic scales. Alcubierre's original calculation required negative energy comparable to the mass energy of entire stars. That immediately reframed the discussion. Warp drive was not forbidden by physics, but it demanded conditions far outside known engineering capabilities. The equations allowed it. Nature, as far as evidence shows, remained silent. Still, the door was not closed. Over the years, physicists refined the model. Harold "Sonny" White, formerly of NASA's Eagle Works laboratory, explored modified warp metrics that reduced energy requirements by altering the shape of the space-time distortion. These models did not remove the need for negative energy, but they showed that the original estimates were not unique. Geometry mattered. Distribution mattered. The problem was not simply too much energy, but how space-time was being asked to bend. Observations of extreme astrophysical environments support this caution. Near black holes, space-time curvature becomes intense, yet remains governed by the same equations. ESA's Gaia mission maps stellar motions near Sagittarius A star, confirming relativistic predictions to high precision. JWST now observes early galaxies whose structures reflect space-time evolution under gravity alone. In all these cases, nature uses curvature sparingly, never approaching the configurations required by a warp bubble. That contrast matters. General relativity allows many solutions that nature does not realize. Closed time-like curves, traversable wormholes, and rotating universes appear in equations but lack observational support. Warp drive may belong to this category, mathematically consistent, physically unattained. Carl Sagan once cautioned, "Extraordinary claims require extraordinary evidence." Warp drive does not yet make a claim, it poses a test. Can space-time be shaped deliberately, or are the allowed solutions merely formal possibilities without physical pathways? Another constraint emerges when causality is examined. Even if a warp bubble moves without local violations, its global structure can create horizons that trap information. Signals from inside may not reach the front edge. Light entering the bubble may accumulate at boundaries. These effects are not guesses. They arise directly from how null geodesics behave in curved spacetime. Photons reveal what equations conceal, and their behavior becomes critical in judging whether a solution can function as more than a static curiosity. History again offers perspective. Nuclear fusion was once a purely theoretical result of quantum mechanics and stellar physics. It took decades before controlled fusion experiments approached practical relevance. Warp drive sits much earlier in that arc. The physics permits discussion. The evidence demands restraint. What makes this topic compelling is not the promise of interstellar travel, but what it reveals about spacetime itself. General relativity does not describe a rigid stage on which events unfold. It describes a dynamic structure that can stretch, compress, and respond. That flexibility explains gravitational lensing measured by ESA's Euclid mission. It explains time dilation measured by atomic clocks in orbit. It explains why the universe's expansion can accelerate without violating local speed limits. Warp drive forces that flexibility into focus. If space-time can expand faster than light during cosmic inflation, if gravitational waves can alter distances across Earth without carrying matter, and if curvature can redirect photons near massive objects, then the real mystery is not why warp-like solutions exist, but why space-time seems so resistant to being shaped at will. The answer may lie in energy conditions, quantum stability, or limits not yet formalized. Or it may lie in the simple fact that mathematics describes more than nature chooses to build. Einstein himself warned against confusing equations with reality. As far as the laws of mathematics refer to reality, they are not certain, he wrote. Warp drive lives precisely at that boundary where certainty fades and structure remains. As this boundary becomes clearer, it turns out that not all signals are equal when space itself is under stress. Among everything we can observe, light remains the most dependable guide to space-time's shape. Photons follow that geometry precisely, and when space is pushed to its limits, their paths show us where motion can and cannot go. Part 2. Why faster than light travel seems impossible in normal space. The most unforgiving number in all of physics is not hidden in a black hole or buried in quantum theory. It is written into every beam of light you have ever seen. No object carrying mass has ever been observed to cross space faster than light, and the reason is not technological, cultural, or historical. It is structural. The universe itself is built so that this limit appears unavoidable. Light in vacuum moves at 299,792 kilometers per second. That number is not an experimental accident. It emerges again and again from entirely different directions of physics. James Clerk Maxwell derived it in the 19th century while unifying electricity and magnetism. Albert Michelson and Edward Morley confirmed it in 1887 when they showed that Earth's motion through space did not alter the measured speed of light. Albert Einstein took the results seriously and realized something unsettling. If every observer measures the same speed for light, then space and time cannot behave the way common sense expects. Special relativity followed from that single insight. Time stretches, length contracts, simultaneity breaks. None of these effects were philosophical claims. They were necessary adjustments demanded by the data. NASA verifies them every day. Atomic clocks aboard GPS satellites tick more slowly than clocks on Earth, by amounts predicted precisely by relativity. Without those corrections, navigation errors would accumulate at roughly 10 kilometers per day. The speed of light is not merely fast. It is the conversion factor between space and time. This is why faster-than-light travel through normal space appears forbidden. As an object accelerates, its energy does not rise smoothly. It increases more steeply with speed, approaching infinity as velocity nears the speed of light. Particle accelerators demonstrate this directly. At CERN, protons reach speeds within a fraction of a percent of light speed, yet require enormous energy increases for diminishing gains. They never cross the boundary. The wall does not yield because it is not a mechanical barrier. It is woven into how space-time responds to motion. Einstein summarized it plainly. Nothing can travel faster than light in vacuum. The sentence is often quoted without its context. He was not proposing a rule to restrict imagination. He was describing what follows when space and time are linked in the way observations demand. General relativity deepened the picture. Gravity, in this framework, is not a force transmitted instantaneously. It is the geometry of space-time itself. Objects follow paths shaped by curvature, not by pulls across empty space. When ESA's Gaia mission measures the deflection of starlight near massive objects, it confirms that light follows curved trajectories because space-time itself is curved. Yet, even here, the speed limit remains intact. Locally, nothing outruns light. This local character matters. Every measurement that enforces the light limit is made in a small neighborhood of space-time. In that neighborhood, physics behaves consistently. The equations that describe energy, momentum, and causality apply without exception. When physicists say faster-than-light travel is impossible, they mean that no object can move through its immediate space-time environment faster than light does in that same environment. History helps clarify why this distinction matters. Before Einstein, physicists believed light propagated through a medium called the luminiferous ether. If Earth moved through that medium, The speed of light should vary depending on direction. Michelson and Morley built an experiment to detect exactly that variation. They found none. The result was not ambiguous. Light speed did not depend on the motion of the source or the observer. That failure forced a radical rethinking of space and time. Einstein did not add complexity. He removed assumptions. Space and time were no longer independent backgrounds. They became part of a unified structure, space-time, where intervals replace absolute measures. Once this step was taken, the speed limit followed naturally. Faster-than-light motion would reverse cause and effect for some observers. Signals could arrive before they were sent. Physics would lose the ability to define consistent sequences of events. This is not speculation. The mathematics shows it directly. If an object could move faster than light through normal space, there would always exist a frame of reference in which the effect precedes the cause. Relativity does not allow preferred frames to rescue this situation. All inertial observers are equivalent. Causality must hold for all, or it holds for none. NASA's studies of high-energy astrophysical phenomena reinforce this picture. Gamma-ray bursts, some of the most energetic events observed, emit photons across a wide range of energies. If faster-than-light effects were available in normal space, higher-energy photons would arrive earlier or later in ways inconsistent with relativity. Observations show no such violations. Photons arrive as predicted, even after traveling billions of years. Yet here the story becomes more subtle. The speed of light looks like an absolute wall only when we assume that motion through space is the only kind of motion available. General relativity allows another possibility. Space itself can change. The expansion of the universe demonstrates this clearly. Distant galaxies recede from us at speeds that increase with distance. Beyond a certain scale, their recession exceeds the speed of light. This is not a violation. Galaxies are not racing through space faster than light. The space between galaxies is stretching. ESA's Planck mission measured the cosmic microwave background with extraordinary precision and confirmed that this expansion has been occurring for over 13 billion years. The distinction is essential. Relativity limits motion through space, not the rate at which space itself can change. This is why cosmic inflation could operate in the early universe. Regions of space separated faster than light, without transmitting signals locally faster than light. Each region obeyed the speed limit in its own neighborhood. This difference often leads to confusion, and confusion invites exaggeration. Faster-than-light travel through normal space remains prohibited. Faster-than-light separation of distant regions through space-time evolution is allowed. The two are not the same phenomenon. Carl Sagan was careful about this point. He once remarked, "We're made of star stuff," but he was equally precise when discussing relativity. He emphasized that the universe permits wonder without abandoning discipline. The speed of light is not a suggestion. It is the backbone of causality. The reason this matters for warp drive is that warp concepts do not propose to outrun light in normal space. They propose to avoid normal space altogether. But before reaching that idea, the impossibility must be understood clearly. Consider energy. In classical mechanics, speed increases linearly with energy. In relativity, the relationship bends sharply. As velocity increases, kinetic energy grows faster than speed. Approaching the speed of light, energy demands diverge. This behavior has been tested repeatedly. No experiment has ever observed a deviation. Consider mass. Relativistic mass increase is often misinterpreted, but the underlying effect is real. Inertia increases with speed. Objects resist acceleration more strongly as they approach light speed. This is not because they become heavier in a naive sense, but because space-time geometry changes how force and motion relate. Consider time. Clocks moving at high speed run slower relative to stationary clocks. This has been measured using particle lifetimes, aircraft-mounted clocks, and satellites. The closer an object gets to light speed, the more time dilation increases. At light speed, proper time for the traveler ceases to advance. These effects are not decorative features of theory. They are constraints. They form a consistent network that leaves no room for shortcuts through normal space. Even quantum mechanics does not rescue the situation. Although quantum entanglement exhibits correlations that appear instantaneous, no usable information travels faster than light. This has been tested in laboratories and confirmed repeatedly. Entanglement preserves causality, precisely because it cannot transmit controllable signals. The lesson is consistent across scales and disciplines. Faster than light travel through ordinary spacetime conflicts with energy conservation, causality, and the structure of spacetime itself. This is why physicists treat the light limit with seriousness rather than frustration. It is not an obstacle to be overcome. It is a clue about how reality is assembled. And yet, the equations of general relativity remain indifferent to intuition. They describe what spacetime can do, not what technology can currently exploit. When solutions appear that reshape distances instead of racing across them, attention naturally shifts. Not because the limit is weak, but because it is precise. Einstein himself acknowledged this openness. The theory decides what we can observe, he said. Relativity forbids certain motions while permitting certain geometries. Understanding the difference requires patience rather than speculation. Normal space enforces the speed of light as an unyielding boundary. Every experiment confirms it. Every observation reinforces it. Every satellite depends on it. That wall does not crack because it is not built from matter or energy. It is built from the structure of spacetime itself. And when that structure is treated not as a passive stage but as something that can respond and change, the focus shifts in a subtle but important way. The limit set by light remains intact, yet the geometry it moves through does not have to stay fixed. Under those conditions, distance itself can be reshaped without anything ever exceeding the speed of light. Part 3. How warp drive avoids outrunning light without violating physics. The most disruptive idea about warp drive is not that it moves fast, but that nothing inside it moves fast at all. That single statement overturns nearly every intuition built from rockets, engines, and acceleration, and it is precisely why warp drive appears in Einstein's equations without tearing relativity apart. In normal space, motion is measured by how quickly an object changes position relative to its surroundings. Speed is distance divided by time, and the speed of light sets the ultimate conversion between the two. Every experiment confirms that no material object can cross that boundary. Warp drive never attempts to. Instead, it changes what distance means. This distinction only becomes clear once spacetime itself is treated as something physical rather than abstract. General relativity does not describe space as a rigid container. It describes a dynamic structure whose geometry responds to energy and momentum. When LIGO detected gravitational waves in 2015, Earth did not move through space to register them. Space itself stretched and compressed by less than 1 part in 10,000 trillion. The detectors were not racing toward a signal. The signal altered the geometry passing through them. Warp drive begins with that same principle. In 1994, Miguel Alcubierre asked a deliberately narrow question. If spacetime can stretch and contract, could it be arranged to do so asymmetrically, compressing space in front of a region while expanding it behind? His solution did not involve thrust or propulsion. It involved geometry. Inside the region, spacetime remained flat and calm. Outside, spacetime changed shape. From the perspective of an observer inside the warp bubble, nothing remarkable happens. The spacecraft does not accelerate. Instruments register no extreme forces. Clocks tick normally. Locally, the ship is at rest. Every measurement obeys special relativity. No photon is overtaken. No signal outruns light. From the perspective of a distant observer, the situation looks entirely different. The bubble itself moves because the geometry around it moves. Distances ahead shrink. Distances behind stretch. The ship appears to cross astronomical separations in less time than light would take through unchanged space. The appearance of faster-than-light travel emerges without any local violation. This is not semantic trickery. It is the same mechanism responsible for cosmic expansion. Galaxies beyond a certain distance recede from us faster than light, yet no galaxy breaks the speed limit in its local frame. ESA's Planck mission confirmed this expansion pattern with extraordinary precision. Warp drive borrows the same principle and applies it on a local scale. What changes is not velocity but topology. The Alcubierre solution demonstrates this cleanly. Spacetime is engineered so that the ship sits inside a region of nearly flat geometry. Ahead of the bubble, space contracts. Behind it, space expands. The bubble rides this distortion like a wave. Importantly, the ship never rides the wave faster than light. It simply stays inside a region where the wave reshapes the path. Physicists paid attention because the mathematics was internally consistent. The solution obeyed Einstein's field equations. It respected local causality. Nothing inside the bubble violated known relativistic limits. That made it fundamentally different from naive, faster-than-light proposals that attempt to accelerate matter beyond light speed. NASA's interest in the concept did not come from engineering optimism, but from theoretical curiosity. Harold White's work at NASA's Eagle Works laboratory examined whether altering the geometry of the bubble could reduce extreme energy requirements. The conclusion was not that warp drive was feasible, but that geometry mattered more than originally assumed. The critical point is this: warp drive does not outrun light because it does not compete with light. There is no race. Light follows geodesics through spacetime. Warp drive changes those geodesics. An analogy helps, but only if treated carefully. Imagine a moving walkway at an airport. A person standing on it is not walking fast. Relative to the walkway, they are nearly stationary. Yet relative to the terminal, they move quickly. The walkway does the work by changing the frame of reference. Warp drive proposes a spacetime version of that idea, with geometry replacing machinery. This analogy breaks down quickly if pushed too far, but it captures the core idea. Motion through spacetime is replaced by motion of spacetime. Observational astronomy reinforces why this is not forbidden. When JWST observes early galaxies formed less than 1 billion years after the Big Bang, it sees structures already separated by enormous distances. Those distances grew because spacetime expanded rapidly. Light traveled locally at its usual speed. The geometry changed around it. Einstein anticipated this flexibility. He warned that geometry could behave in unintuitive ways, once freed from Newtonian assumptions. Still, he remained cautious. He did not claim that all mathematical solutions correspond to physical realities. Manidonot. Warp drive occupies that uncertain territory. One immediate consequence of removing the race is that acceleration disappears. Traditional spacecraft impose extreme g-forces when accelerating to high speed. Warp drive avoids this entirely. The ship remains locally inertial. No crew is pressed against walls. No structural stress arises from acceleration. This feature is not decorative, it is necessary. Relativity links acceleration to inertia and energy. Avoiding acceleration avoids many of the usual relativistic penalties, but this advantage reveals a deeper cost. To reshape spacetime itself, energy must be distributed in very specific ways. The Alcubierre solution requires regions of negative energy density surrounding the bubble. This requirement is not negotiable within the original framework. It emerges directly from how curvature responds to energy in Einstein's equations. Negative energy is not imaginary. Quantum field theory allows small, temporary violations of classical energy conditions. The Casimir effect demonstrates this experimentally. However, the scale is microscopic. Warp drive demands macroscopic, stable regions of negative energy, arranged with precision. NASA's own analyses emphasize this gap. No known process can produce or sustain the required energy configurations. This is not a technical hurdle. It is a fundamental unknown. Still, the conceptual separation between motion and geometry remains valid regardless of feasibility. It teaches something profound about why the speed of light is not simply a speed, but a structural constant. Light does not merely travel fast. It defines how space-time connects events. Warp drive avoids violating that definition by refusing to move through the structure light defines. Instead, it reshapes the structure itself. Carl Sagan understood the importance of such distinctions. He often emphasized that the universe is not obliged to conform to intuition, but it is obliged to obey its own rules. Warp drive does not rebel against those rules. It explores their edges. Another subtle consequence emerges when observers consider horizons. In a warp bubble, the front edge can become causally disconnected from the interior. Signals from inside may not reach the boundary. Light emitted forward can accumulate without escaping. This creates a form of horizon similar to those studied in black hole physics. These effects are not speculative. They arise naturally from how light propagates in curved spacetime. Photons follow paths determined by geometry. When geometry changes sharply, photon behavior changes sharply. ESA's studies of gravitational lensing show this clearly on cosmic scales. Light bends around clusters of galaxies because spacetime bends. Warp drive would impose a far more extreme version of this effect on a local scale. The deeper implication is unavoidable. Avoiding faster than light motion does not mean avoiding relativistic consequences. It means trading one set of constraints for another. History suggests caution. Wormholes, rotating universes, and closed time-like curves all appear in Einstein's equations. None have observational support. Warp drive may join them as a solution that reveals the flexibility of spacetime without revealing a pathway to construction. Yet, dismissing it entirely would miss the lesson. Warp drive clarifies why the light limit exists and what it actually governs. It is not a ban on ambition. It is a statement about local causality. By removing the race, warp drive exposes the architecture of spacetime more clearly than any rocket equation ever could. The universe allows distances to change. It forbids objects from cheating within their local neighborhoods. That balance is not arbitrary. It preserves cause and effect while permitting cosmic evolution. As the focus shifts away from raw speed and toward geometry, the problem quietly rearranges itself. Engines matter less than curvature, and motion no longer means what it once did. If distance can be reshaped without violating the light limit, then the real constraint may lie elsewhere in how light behaves inside distorted spacetime, especially near the boundary of a warp bubble. Part 4. What actually moves in a warp drive if the ship stays locally still? The most unsettling realization in warp drive physics is that the spacecraft is not the thing in motion. That statement sounds wrong at first hearing, because every form of travel we know involves an object changing position through space. Rockets burn fuel, gain velocity, and cross distance by moving within a fixed background. Warp drive breaks that picture completely. The ship does not traverse space. Space reorganizes itself around the ship. To understand why this matters, it helps to return to how motion is defined in general relativity. In Einstein's framework, position and time are not measured against an absolute backdrop. They are measured relative to spacetime itself, which is shaped by energy and momentum. Objects do not simply move along straight lines. They follow the shortest available paths through curved geometry. These paths, called geodesics, define what motion even means. When NASA and ESA track spacecraft navigating the solar system, they already account for this geometry. Signals sent to Mars probes arrive later than Newtonian physics would predict because spacetime near the Sun is curved. This delay, first measured during radar experiments in the 1960s, confirmed that spacetime geometry alters distances and travel times without anything unusual happening to the spacecraft itself. The probe followed a normal path. Space was not flat. Warp drive pushes that idea to an extreme. In the Alcubierre model, the ship remains on a geodesic that is locally flat. Inside the warp bubble, spacetime is arranged so that the usual rules of inertia apply. No acceleration is detected. No internal forces appear. The ship's trajectory through its immediate surroundings looks indistinguishable from being parked in deep space. What changes is the geometry outside that region. Ahead of the bubble, spacetime contracts. Behind it, spacetime expands. The ship remains centered in a region where geometry is stable, while the surrounding spacetime changes shape. The bubble itself moves because the distortion moves, not because the ship gains velocity. This distinction is not cosmetic. It determines what quantities are conserved and what physical laws remain intact. Energy, momentum, and causality are defined locally. Inside the bubble, all local measurements obey special relativity. Clocks tick normally. Light behaves as expected. Nothing ever exceeds the speed of light in its own neighborhood. From far away, the situation looks entirely different. The distance between the ship and its destination shrinks because the metric defining that distance changes. Observers may measure an effective speed greater than light when comparing endpoints, but that comparison mixes regions with different spacetime geometry. No local observer ever sees a violation. This is exactly how cosmologists describe the expanding universe. When ESA's Planck mission mapped the cosmic microwave background, it revealed a universe whose large-scale geometry evolves with time. Distant galaxies recede not because they move rapidly through space, but because space between them grows. The galaxies themselves remain locally slow. Warp drive borrows this mechanism and applies it deliberately. So what actually moves? The answer is the metric itself. The mathematical object that defines distances and durations changes as the bubble propagates. In practical terms, this means rulers laid ahead of the ship would shorten, while rulers behind would lengthen. Clocks placed in different regions would desynchronize according to curvature, even if each clock behaved normally where it sat. This behavior is not hypothetical. Gravitational waves demonstrate it directly. When LIGO detected spacetime ripples from merging black holes, the mirrors did not move through space to record the signal. The distance between them changed because spacetime stretched and compressed. The mirrors stayed locally still. The geometry moved. Warp drive replaces transient ripples with a sustained distortion. Physicists often emphasize that spacetime geometry is not an object in the usual sense. It does not have substance or texture, but it does have measurable consequences. Light follows it. Matter responds to it. Time depends on it. When geometry changes, everything built on it responds. NASA's Gravity Probe B mission measured how Earth's rotation slightly drags spacetime around it. The effect was tiny, but detectable. Space near Earth did not move like a fluid, yet its geometry shifted enough to alter gyroscope orientations. This phenomenon, called frame dragging, shows that spacetime can behave dynamically without carrying mass or energy in the ordinary sense. Warp drive relies on this dynamism. If the ship stays locally still, then navigation becomes a question of shaping geometry rather than applying thrust. The ship does not aim itself by acceleration. It is carried along by the evolving shape of spacetime. Direction is determined by where contraction occurs. Speed is determined by how rapidly the distortion propagates. This leads to a critical implication. The ship cannot control its motion in the way a conventional vehicle does. It cannot simply slow down by braking. To stop, the geometry must be relaxed back to flat spacetime. To turn, the distortion must be reshaped asymmetrically. Here, theoretical work reveals complications. The Alcubierre bubble has boundaries where curvature changes sharply. These boundaries behave like moving horizons. Light approaching from certain directions cannot cross them. Information from inside may not influence the front edge. This means the ship may not be able to steer itself once the bubble is established. This result is not philosophical. It emerges from calculations of how null paths behave in curved spacetime. Photons reveal geometry with uncompromising honesty. If a photon cannot escape a region, neither can a command signal. ESA's studies of black hole environments show similar behavior. Near an event horizon, spacetime curvature prevents signals from escaping outward. Warp bubbles exhibit horizon-like features even without singularities. The geometry itself enforces causal separation. This raises a subtle but crucial point. If the ship is not moving, then its occupants are not the agents of motion. The spacetime configuration is. Control shifts from onboard systems to whatever mechanism generates and maintains the distortion. Physicists take this seriously because it suggests that warp drive is less like piloting and more like releasing a carefully shaped instability. Once initiated, the geometry follows its own rules. Adjusting it requires interaction with regions that may be causally inaccessible. The story echoes earlier lessons from physics. Nuclear chain reactions taught scientists that initiating a process and controlling it are very different challenges. The mathematics may permit a configuration, but stability and control demand additional constraints. NASA's cautious assessments reflect this understanding. Warp drive studies focus not on speed claims, but on geometry, energy conditions, and stability. No experimental program assumes that keeping a ship locally still solves the hard problems. It merely relocates them. Another implication follows. If spacetime moves and the ship does not, Then inertial effects disappear. This eliminates many dangers of high-speed travel. It also removes familiar feedback. The crew would not feel motion. Instruments measuring acceleration would read 0. Only external observations would reveal progress. This disconnect between local experience and global displacement is rare but not unprecedented. Astronauts aboard the International Space Station orbit Earth at roughly 7 kilometers per second. Inside the station, they float freely, experiencing weightlessness. Locally, they feel still. Globally, they circle Earth every 90 minutes. Warp drive amplifies this separation between local and global perspectives. The difference is scale and mechanism. Orbital motion still involves velocity through space. Warp motion does not. It replaces velocity with evolving geometry. Carl Sagan often stressed that perspective matters in science. The same event can look different depending on where one stands. Warp drive formalizes that idea. From inside, nothing happens. From outside, something extraordinary appears to occur. This duality explains why warp drive feels paradoxical. It violates intuition built from everyday motion, while obeying the deeper rules that govern spacetime. Yet the cost remains severe. Generating and sustaining the required geometry demands energy distributions unlike anything observed in nature. Negative energy densities appear unavoidable in known solutions. Quantum effects provide only microscopic hints of such behavior. JWST's observations of early galaxies remind us how conservative nature usually is. Even in the most extreme environments, space-time curvature remains tied to mass and energy in familiar ways. No region exhibits deliberate, engineered distortions on macroscopic scales. This does not prove impossibility. It highlights rarity. Warp drive teaches a precise lesson. Motion is not always about objects changing position. Sometimes it is about the stage itself changing shape. In such cases, asking what moves requires abandoning habits formed in flat space. What moves is the geometry that defines distance. What stays still is the ship that inhabits a protected region of that geometry. And what limits the entire process is not speed, but the ability to sculpt spacetime without losing causal control. When spacetime itself is allowed to move while matter remains locally at rest, the problem narrows rather than disappears. Geometry alone is no longer enough. What matters is how light behaves at the boundaries of that motion, where curvature becomes steep and signals face their first real limits. Part 5. How light behaves inside a warp bubble. The most unforgiving judge of a warp drive is not energy, mass, or mathematics, but light itself. Equations can suggest possibilities, but photons expose every hidden weakness the moment spacetime begins to bend. In physics, light is never just illumination. It is measurement. It defines distance, synchronizes clocks, and reveals geometry with absolute precision. Every claim about spacetime must ultimately answer to how photons move, because photons do not negotiate. They follow the structure they are given. This is why warp drive theory becomes most fragile when light enters the picture. In ordinary space, light travels along the straightest possible paths allowed by geometry. In flat spacetime, those paths appear straight. Near massive objects, they curve. ESA's observations of gravitational lensing show this clearly. Light from distant galaxies bends as it passes massive clusters, creating arcs and multiple images. The galaxies do not move. The light does not slow down. The geometry changes, and photons respond. A warp bubble introduces curvature far more extreme than anything observed naturally outside black holes. Inside the bubble, spacetime is designed to remain nearly flat. Outside, it is sharply distorted. At the boundary, the geometry transitions rapidly, and it is here that photons reveal the true cost of warp motion. Consider a photon emitted inside the bubble toward the front edge. Locally, it travels at the usual speed of light. Nothing unusual happens at emission. But as it approaches the boundary, spacetime ahead is contracting. Distances shrink faster than the photon can traverse them. From the perspective of the interior, the photon slows relative to the boundary, even though it never slows locally. This effect is not metaphorical. It arises directly from how distances are defined in curved spacetime. The photon continues to move at light speed in its local frame, but the frame itself is changing. The boundary retreats faster than the photon can reach it. The result is stark. Light emitted forward inside a sufficiently strong warp bubble may never escape. It accumulates near the front edge, compressed into a thin region of intense energy density. This behavior resembles the formation of horizons studied in black hole physics. NASA's studies of event horizons show similar principles at work. Near a black hole, light emitted outward appears frozen at the horizon to distant observers. The photon never outruns the geometry pulling it back. Warp bubbles reproduce this effect without requiring a singularity. Now consider light approaching the bubble from the outside. As a photon enters the region of distorted spacetime, its path bends sharply. Depending on the bubble's shape, the photon may be deflected, trapped, or blue-shifted to extreme energies. Calculations show that incoming light can pile up at the rear boundary as spacetime expands behind the bubble. This accumulation matters. Photons carry energy and momentum. When concentrated, they exert pressure. In ordinary situations, radiation pressure is small but measurable. NASA uses it to model solar sail behavior and spacecraft thermal dynamics. Inside a warp bubble, photon accumulation could become severe. The equations do not forbid this buildup. They predict it. This creates a profound challenge. If light cannot pass freely across the bubble boundary, neither can information. Signals sent forward from inside may never reach the front. Signals from outside may never penetrate the interior. The bubble becomes causally isolated in certain directions. Physicists refer to this as a horizon problem. It is not a matter of communication delay, it is a matter of causal disconnection. Once established, the bubble may be unable to receive commands to alter its shape or shut itself down from within. This is not speculation. It follows from how null paths behave in curved spacetime. Null paths are the trajectories photons follow. Their behavior is well understood and has been confirmed repeatedly by observation. ESA's work on relativistic jets near supermassive black holes shows how light can become trapped, collimated, and redirected by spacetime geometry alone. Warp drive proposals would need to manage similar effects deliberately, not accidentally. The photon problem exposes another constraint. Light inside the bubble behaves normally only as long as the interior remains flat. Any asymmetry introduces gradients that photons immediately reveal. Unlike matter, photons do not average over forces. They respond instantly to curvature. This sensitivity is why light is used to test general relativity so rigorously. From the Pound-Rebka experiment, measuring gravitational redshift to modern satellite-based clock comparisons, photons have consistently validated Einstein's predictions. Warp drive must satisfy the same scrutiny. Another effect emerges when considering frequency shifts. As photons climb out of curved spacetime, their frequencies change. In a warp bubble, photons approaching regions of expansion may redshift dramatically, losing energy. Photons approaching contraction may blueshift, gaining energy. In extreme cases, calculations suggest incoming cosmic background radiation could be blueshifted to hazardous levels at the front boundary. The cosmic microwave background, measured precisely by ESA's Planck mission, bathes all of space at a temperature of about 2.7 Kelvin. Under warp compression, those low-energy photons could be shifted upward by enormous factors. This is not a trivial detail. Radiation hazards scale with energy, not intensity alone. Even a sparse photon field can become dangerous if blue-shifted sufficiently. NASA analyses have flagged this as a serious obstacle. A warp bubble traveling through interstellar space would encounter background radiation, starlight, and high-energy particles. All would interact with a distorted geometry in complex ways. The equations do not promise protection. They describe consequences. Inside the bubble, observers might remain unaware until photons trapped at the boundary are suddenly released when the geometry relaxes. The energy stored in those trapped photons could be catastrophic. These insights did not come from speculative fiction. They emerged from careful studies of photon trajectories in curved spacetime. Physicists traced how light would move using the same tools used to predict lensing and horizon behavior near black holes. The lesson is consistent. Light is not an accessory. It is the diagnostic. Carl Sagan often emphasized that understanding comes from asking what observations would show, not from trusting elegant ideas. In this case, photons are the observers. They report faithfully on space-time shape. Another subtlety arises inside the bubble. Even if the interior is flat, clocks inside must remain synchronized with clocks outside if navigation is to be meaningful. Light signals are the only way to compare time across regions. If those signals cannot cross boundaries symmetrically, synchronization fails. Timekeeping is not optional. GPS systems demonstrate this daily. Without continuous photon exchange between satellites and Earth, positioning collapses. Warp drive introduces regions where photon exchange is asymmetric or impossible. This undermines one of the most attractive features of warp concepts. The ship may remain locally calm, but it becomes globally blind. ESA's deep space communication studies show how sensitive navigation is to signal delay and distortion. Even small relativistic effects require correction. Warp bubbles impose distortions orders of magnitude larger. The behavior of light also constrains how the bubble forms and dissipates. During formation, photons crossing the region experience rapidly changing curvature. This can generate particle production effects analogous to those studied in cosmological horizons. Quantum field theory predicts that rapidly changing spacetime can create particles from vacuum fluctuations. These effects are subtle but real. They are studied in early universe cosmology and black hole evaporation. Warp drive proposals would need to account for them explicitly. Despite these challenges, light does not forbid warp drive outright. It clarifies the cost. Photons show that avoiding faster-than-light motion does not avoid extreme relativistic behavior. It simply relocates it to boundaries where geometry changes abruptly. The elegance of warp drive lies in its respect for local limits. Its fragility lies in the global behavior of light. This is why physicists say that photons expose what equations hide. The equations allow solutions. Photons test them. Every confirmed observation of spacetime curvature, from gravitational lensing to time dilation, reinforces this lesson. Geometry is not free to behave arbitrarily. It is accountable to how light moves. Warp drive sits at that accountability boundary. It survives only as long as photon behavior remains physically manageable. When light fails to move freely across a warp bubble's boundary, the problem can no longer be contained within geometry alone. Sustaining that structure requires energy conditions unlike anything produced by ordinary matter. At that point, the discussion inevitably turns toward more extreme requirements, the kinds of energy needed to shape spacetime strongly enough to confine photons at all. Part 6. Why warp drive requires exotic or negative energy. The moment warp drive stops being a geometric curiosity and starts behaving like a physical system, one requirement appears with brutal clarity. Ordinary matter cannot do the job. Every confirmed model that bends spacetime strongly enough to mislead light demands something nature has never allowed us to handle at scale: energy arranged in ways that violate the habits of familiar matter. In general relativity, spacetime does not bend arbitrarily. Curvature responds directly to energy and momentum. This relationship is not philosophical. It has been tested for more than a century. When NASA tracks how light skims the sun during eclipses, when ESA measures gravitational lensing by galaxy clusters, when JWST maps distorted images of distant galaxies, all those observations confirm the same rule. Positive energy density curves spacetime inward. Matter pulls geometry toward itself. Warp drive demands the opposite in critical regions. To create a warp bubble, spacetime must contract in front of the ship and expand behind it. Contraction can be produced by positive energy. Expansion of the required form cannot. The equations insist that, in some regions, energy density must be negative relative to the surrounding vacuum. Not low, not sparse. Negative. This requirement does not come from engineering optimism or pessimism. It falls directly out of Einstein's equations when the Alcubierre geometry is examined carefully. The stress-energy distribution required to sustain the bubble includes terms that no configuration of ordinary matter can supply. Physicists describe this constraint using energy conditions. These are mathematical statements about how energy behaves in realistic systems. For decades, they were treated as almost self-evident. Energy density is non-negative. Energy flows do not exceed certain bounds. These assumptions matched every known form of matter and radiation. Warp drive breaks them. The first reaction was skepticism. Negative energy sounded like a mathematical artifact rather than a physical possibility. But quantum field theory complicated the picture. In the quantum vacuum, energy is not simply zero, it fluctuates. And under specific conditions, those fluctuations can dip below the average vacuum level. The Casimir effect provided the first clear demonstration. Two uncharged metal plates placed extremely close together experience an attractive force. This force arises because the allowed vacuum modes between the plates differ from those outside. The energy density between the plates is lower than the surrounding vacuum. In precise terms, it is negative relative to the ambient vacuum energy. This effect has been measured repeatedly in laboratories and agrees with quantum theory to high precision. It proves that negative energy densities are not forbidden outright. But scale matters. The Casimir effect produces negative energy densities over distances measured in micrometers, with magnitudes far too small to curve spacetime appreciably. Warp drive requires negative energy spread over macroscopic regions, arranged with exquisite precision and sustained over time. NASA's own technical assessments emphasize this gap. Quantum effects allow small violations of classical energy conditions, but they are tightly constrained. They are fleeting. They cannot be amplified arbitrarily without destabilizing the vacuum itself. This leads to a deeper problem. Quantum field theory does not merely permit negative energy, it polices it. So-called quantum inequalities limit how much negative energy can exist, for how long, and over what volume. The more negative the energy, the shorter its allowed duration. Warp drive models collide head-on with these limits. Physicists have explored whether clever geometries could reduce the required negative energy. Modifications to the Alcubierre bubble redistribute curvature, flattening gradients and shrinking problematic regions. Some calculations show dramatic reductions in total energy requirements. Yet none eliminate the need for negative energy entirely. This persistence is telling. It suggests the requirement is structural rather than incidental. Nature offers no examples of stable, macroscopic regions dominated by negative energy. Even in extreme astrophysical environments near neutron stars, black holes, or the early universe, energy densities remain positive in the classical sense. ESA's observations of compact objects confirm this repeatedly. The early universe does provide one apparent exception. During cosmic inflation, spacetime expanded at an extraordinary rate. The energy driving that expansion behaved unlike any familiar substance. Yet even here, the energy density remained positive. It was the pressure that was negative, not the energy itself. This distinction matters. Inflation stretches space, but does not create the specific curvature pattern required by a warp bubble. Warp drive requires a more surgical manipulation of spacetime. To understand why ordinary matter fails, consider how matter behaves under compression. As density increases, pressure rises. This pressure contributes to spacetime curvature, just as mass does. Positive pressure reinforces gravitational attraction. Warp drive requires regions where pressure and energy combine to produce repulsion in a controlled way. No known state of matter does this reliably. Even exotic astrophysical states fall short. Neutron-degenerate matter resists compression fiercely, but it still produces attractive gravity. Quark matter, if it exists, behaves similarly. Dark energy drives cosmic acceleration, but it is uniformly distributed and cannot be shaped locally. NASA and ESA observations show dark energy acting on the largest scales, influencing the expansion of the universe as a whole. It does not cluster, it does not form gradients. Warp drive demands precisely those gradients. This mismatch is not merely technological, it is conceptual. Warp drive asks spacetime to curve in ways that violate the expectations encoded in quantum field theory and classical gravity simultaneously. Some researchers have asked whether negative mass could exist. Negative mass would respond to forces in reversed ways, potentially providing the needed curvature. But negative mass introduces immediate instabilities. Paired with positive mass, it leads to runaway motion that violates conservation principles. No experimental evidence supports its existence. Carl Sagan once warned that The universe is not required to be in perfect harmony with human ambition. Negative energy may exist only within narrow quantum tolerances, not as a tool for engineering geometry. The problem deepens when stability is considered. Even if negative energy could be assembled, it would resist confinement. Quantum fluctuations would tend to equalize energy densities, erasing sharp gradients. Maintaining a warp bubble would require continuous input of precisely arranged energy, counteracting natural relaxation processes. NASA's studies of quantum vacuum behavior emphasize how delicate these effects are. The vacuum is not passive, it reacts. Disturb it strongly, and it responds with particle creation, radiation, and instabilities. This is not speculation. Hawking radiation near black holes arises from similar principles. Rapid changes in space-time geometry generate real particles. Warp drive would impose even more extreme gradients over larger regions. Photons trapped at the bubble boundary, discussed earlier, would contribute additional energy densities. Those photons would interact with the negative energy fields required to sustain the bubble, creating feedback loops that no current theory knows how to stabilize. The conclusion emerges slowly but firmly. Warp drive is not blocked by a single wall. It is constrained by an entire network of physical principles that all point in the same direction. Negative energy exists, but only barely. Quantum vacuum effects allow it, but forbid its abuse. Space-time can bend dramatically, but only when energy behaves within narrow bounds. Light can be guided by geometry, but it punishes excessive distortion with horizons and instabilities. Warp drive asks for all these limits to be approached at once. This does not make the concept meaningless. It makes it diagnostic. By exploring why exotic energy is required, physicists learn which features of space-time are flexible and which are rigid. NASA's cautious language reflects this perspective. Warp drive research is not about promising faster than light travel. It is about probing the deep relationship between geometry, energy, and quantum structure. Every attempt to remove negative energy from the equations has failed so far. That failure is informative. It suggests that space-time resists being reshaped in ways that preserve local calm while imposing global distortion. The universe allows curvature, it allows expansion, it allows horizons. But it does not easily allow deliberate manipulation of these features on demand. Once exotic energy enters the picture, the discussion shifts in a more fundamental direction. The challenge is no longer producing such energy, but understanding what its presence would do to the structure of physical law itself. Energy conditions, stability, and the preservation of cause and effect all come under pressure, raising a deeper concern about whether a warp drive could exist at all without violating principles that physics relies on to remain consistent. Part 7. Can warp drive exist without breaking energy laws? The most uncomfortable question in the entire warp drive discussion is not how fast it could travel, but whether it can exist at all without quietly tearing apart the rules that keep the universe consistent. Every modern warp proposal begins with a promise to respect energy laws, and almost everyone ends by circling back to the same difficulty. The escape routes look convincing on paper, yet collapse on a closer inspection. Energy laws are not optional guidelines. They are among the most thoroughly tested principles in physics. Conservation of energy is confirmed every time a spacecraft performs a gravity assist, every time a particle collision is analyzed at CERN, every time NASA balances fuel budgets for interplanetary missions. Energy does not disappear. It does not appear from nowhere. It changes form, moves between systems, but the accounting always closes. General relativity complicates this picture, but it does not abolish it. In curved spacetime, defining global energy becomes subtle, yet local energy conservation remains intact. ESA's precision tests of orbital dynamics around Earth and other planets rely on this consistency. Even in strong gravitational fields, energy behaves predictably when measured locally. Warp drive challenges this predictability in an indirect way. The Alcubierre solution does not explicitly violate conservation of energy. It does not demand infinite energy output or perpetual motion. Instead, it violates the conditions under which energy behaves in familiar ways. These conditions, known as energy conditions, are assumptions about how energy density and pressure relate in physically reasonable systems. For decades, These conditions were treated as nearly inviolable because they matched every known form of matter and radiation. Positive energy density, causal energy flow, no observer measuring negative total energy along their trajectory. These assumptions underlie many theorems in relativity, including those that prevent time paradoxes and unstable geometries. Warp drive violates several of them. This realization prompted a wave of research aimed at salvaging the concept without discarding energy laws entirely. If the exotic energy requirement could be minimized, confined, or reinterpreted, perhaps warp geometry could survive within acceptable bounds. One strategy involved reshaping the warp bubble. By smoothing sharp gradients and redistributing curvature, researchers found that total energy requirements could be reduced dramatically. Instead of a thin shell of extreme negative energy, the distortion could be spread out more gently. In some models, the required energy dropped by many orders of magnitude. NASA's interest in these refinements was cautious. Reducing energy requirements is not the same as eliminating forbidden conditions. A smaller violation remains a violation. Another approach explored dynamic bubbles rather than static ones. Instead of maintaining a permanent distortion, the geometry could evolve over time, potentially relaxing quantum constraints. In these scenarios, the warp bubble forms, propagates briefly, and dissipates. Yet calculations showed that quantum inequalities still apply. Negative energy cannot be stockpiled or stretched arbitrarily in time. Shorter durations allow larger magnitudes, but warp travel over meaningful distances requires persistence. The mathematics closes the window as soon as duration becomes macroscopic. A third proposal looked to reinterpret what negative means. In curved spacetime, energy can appear negative relative to certain observers while remaining positive in others. Perhaps warp drive only exploits this relativity of measurement. This idea fails under scrutiny. Energy conditions are formulated to be observer-independent in crucial ways. If a configuration violates them for any observer following a physical trajectory, the violation is real. Photons, again, act as witnesses. Their trajectories reveal whether energy flow respects causal structure. ESA's observations of high-energy astrophysical jets illustrate this point. Even in extreme environments, energy flows remain causal. No configuration observed in nature produces the sustained violations warp drive demands. Some researchers turn to semi-classical gravity, where quantum fields interact with classical spacetime. Perhaps quantum effects could stabilize warp geometry. The vacuum, after all, already supports exotic phenomena. But semi-classical analyses introduce new instabilities. Strong curvature couples to quantum fields, producing particle creation. Energy extracted from the vacuum reappears as radiation. Instead of sustaining a warp bubble, the system radiates itself apart. This is not hypothetical. Similar effects are studied in black hole evaporation and early universe cosmology. Rapidly changing geometry is a source of energy redistribution, not a free resource. The deeper issue emerges when causality is considered alongside energy. Energy conditions are not arbitrary restrictions. They exist to protect causal order. Violating them often allows closed loops of influence, where cause and effect lose their sequence. Warp drive geometry skirts this edge. While local motion remains subluminal, global paths can connect distant events unusually quickly. In certain configurations, this opens the door to causal paradoxes unless energy conditions intervene. Physicists have shown that enforcing reasonable energy conditions prevents these paradoxes. Relaxing them reintroduces them. Warp drive proposals that avoid energy violations often do so by sacrificing controllability or introducing horizons that isolate regions causally. The cost is hidden, not removed. JWST's observations of the early universe provide an instructive contrast. Inflation expanded space rapidly, yet energy conditions remained satisfied in subtle ways. The expansion did not allow local violations of causality or energy conservation. The universe remained internally consistent. Warp drive attempts to compress that cosmic scale behavior into a local, directed process. The laws resist. Carl Sagan often emphasized that nature is subtle, but not malicious. When multiple independent principles converge on the same conclusion, it deserves attention. Energy conditions, quantum inequalities, photon behavior, and causal structure all converge here. The illusion of escape arises because mathematics permits many formal solutions. Physics filters them. This filtering is not based on taste or conservatism. It is based on accumulated evidence. Every observed system respects the same constraints warp drive strains against. From laboratory-scale experiments to cosmic surveys, the pattern is consistent. That does not mean warp drive is disproven. It means its survival depends on discovering new physics that reshapes these constraints without breaking the coherence of the whole framework. NASA and ESA research programs approach this cautiously. They do not treat warp drive as an engineering goal, but as a stress test for fundamental theory. By asking whether it can exist without breaking energy laws, physicists learn where those laws are strongest and where they might bend. So far, every bending introduces cracks elsewhere. Energy can be rearranged, but not arbitrarily. Geometry can change, but not freely. Quantum effects permit exceptions, but only briefly and locally. Warp drive demands all three concessions simultaneously. This convergence is not encouraging, but it is informative. The universe appears to allow extraordinary structures only when they emerge naturally from its own evolution. Artificial imposition of such structures meets resistance encoded in the laws themselves. When attempts to satisfy energy conditions lead inevitably to horizons, instabilities, or regions cut off from the rest of spacetime, the problem deepens. The concern is no longer confined to energy or geometry. What comes under strain is the consistency of cause and effect itself, and whether a system like this could maintain a coherent ordering of events across time. Part 8. Would warp drive break causality, or the order of time? The most dangerous consequence of warp drive is not its energy demand or its instability, but the quiet way it threatens the sequence of events themselves. The moment spacetime geometry allows distances to collapse faster than light can traverse them, the distinction between before and after stops being guaranteed by structure alone. Causality is not an abstract preference of physicists. It is a property verified every time an experiment is repeated, every time a signal is sent and received, every time a spacecraft command arrives after it is transmitted. NASA's deep space missions depend on this ordering. Signals sent to Voyager, now more than 24 billion kilometers away, arrive hours later, not earlier. ESA's communication with probes at Mars relies on the same certainty. Cause precedes effect. Always. Special relativity embeds this ordering into spacetime itself. Events are arranged within light cones. Inside the cone, influence is possible. Outside it, influence is forbidden. This structure is not imposed by philosophy. It emerges from the invariance of the speed of light, confirmed by more than a century of experiments. Warp drive appears to respect this locally. Inside the bubble, nothing outruns light. Signals move normally. Clocks tick in step. But causality is not purely local, it is global. It concerns how events relate across spacetime, not just within a small region. Here, geometry becomes decisive. In general relativity, spacetime can curve so strongly that paths connecting distant events become shorter than expected. If those paths allow influence to propagate between events that would otherwise be space-like separated, then causality is altered, even if no local speed limit is violated. This is not a speculative statement. Physicists have shown it mathematically. In the late 20th century, researchers studying hypothetical space-time geometries discovered that faster-than-light effective travel allows closed loops of influence under certain conditions. These loops are known as closed time-like curves. Along such paths, an event can influence itself in its own past. Einstein himself was troubled by these possibilities. Although his equations permit such solutions, he doubted their physical relevance. Later, work reinforced his caution. Stephen Hawking proposed what he called the chronology protection conjecture, arguing that the laws of physics may prevent macroscopic violations of causal order. Warp drive geometries bring this issue into focus. If a warp bubble can connect distant regions faster than light would through normal space, then observers in different frames may disagree on the order of events. In some frames, arrival could precede departure. This is not a trick of language. It is a direct consequence of Lorentz transformations applied to spacetime with superluminal effective connections. Physicists have demonstrated that combining faster-than-light travel with ordinary relativistic motion allows the construction of causal loops. One does not need exotic time machines. The geometry alone suffices. This is why energy conditions matter so much. They are not merely bookkeeping rules. They are safeguards against geometries that permit such loops. Violating them opens doors that mathematics alone does not close. NASA's reliance on relativistic causality is absolute. Every navigation algorithm assumes consistent event ordering. Even small ambiguities would render guidance impossible. The universe, as observed, does not tolerate such ambiguities. General relativity allows curved spacetime, but observations show that nature avoids configurations that enable causal loops. No astrophysical system observed by JWST, ESA, or NASA exhibits closed time-like behavior. Black holes curve spacetime intensely, yet their horizons preserve causal order rather than destroy it. Warp drive occupies a more precarious position. It creates horizons not tied to mass collapse, but to engineered geometry. These horizons isolate regions and can produce asymmetric causal access. Signals may enter but not exit, or vice versa. This asymmetry matters. If an observer can influence a region without being influenced in return, the mutual consistency of event ordering weakens. Causality becomes conditional rather than absolute. Physicists analyzing warp metrics found that avoiding such paradoxes requires severe restrictions. The bubble must be configured so that no observer can use it to create closed loops. These restrictions often render the bubble uncontrollable or unusable for round trips. Once again, the escape seems illusory. History provides a useful comparison. In the 1950s, solutions describing rotating universes were discovered. These universes allowed closed time-like curves everywhere. Yet no evidence supports their existence. Observations of cosmic microwave background isotropy, measured precisely by ESA's Planck mission, rule them out. Nature appears to select geometries that preserve global order. Carl Sagan often reminded audiences that extraordinary ideas must survive contact with reality. Warp drive's contact point is causality. And here, reality resists. Even if a single warp journey could be arranged without paradox, multiple journeys introduce complications. Two bubbles moving relative to each other could form a causal loop even if each alone is safe. This fragility suggests that the underlying geometry is unstable under repetition. Quantum theory adds another layer. Quantum fields propagating in spacetime sensitive to causal structure can become unstable when closed loops are possible. Calculations show that vacuum fluctuations diverge near such geometries. Energy densities explode. The spacetime tears itself apart. These results echo Hawking's conjecture. The universe appears to react violently to attempts to reorder time. NASA's studies of semi-classical gravity emphasize this feedback. Geometry influences quantum fields, and quantum fields influence geometry. Causality violations trigger runaway effects that restore consistency by destroying the configuration. This is not a moral judgment by the universe. It is a dynamical response. Warp drive thus faces a dilemma. Preserve causality, and the geometry becomes tightly constrained, likely unusable. Relax constraints and instabilities emerge that erase the configuration. The pattern is familiar by now. Every attempt to bypass a foundational principle encounters multiple independent barriers. This does not trivialize the exploration. It deepens it. By testing warp drive against causality, physicists sharpen their understanding of why time has an order at all. The arrow of time is not merely thermodynamic. It is encoded into spacetime structure. JWST's observations of early galaxy formation reinforce this. Structures form, evolve, and age in consistent sequences. Light from the past arrives reliably. The universe remembers its history. Warp drive threatens to blur that memory. Einstein once wrote, "The distinction between past, present, and future is only a stubbornly persistent illusion." He meant this within the block universe interpretation of relativity, where time is a dimension like space. Yet even in this view, causal relations remain consistent. Events are ordered within the block. Warp drive risks rearranging that order. This is why physicists treat the causality question as decisive. Energy might be engineered, geometry might be sculpted. But if the result undermines the consistency of event ordering, the configuration cannot represent a stable physical process. NASA and ESA do not frame this as a prohibition. They frame it as a constraint revealed by observation. The universe has operated for 13.8 billion years without observable causal violations. Any proposal that predicts them must explain why they do not already occur. So far, warp drive has not met that burden. If causality cannot be bent without consequence, then even a flawlessly engineered warp bubble would face limits that go beyond design. The difficulty shifts toward interaction itself. Questions of detection, control, and access emerge, shaped by horizons and the way information can or cannot move between warped spacetime and the surrounding universe. Part 9. Can a warp drive be controlled, observed, or even entered? The most unsettling problem with warp drive is not how to build it, but how to interact with it at all. A system that reshapes spacetime so strongly that light cannot cross its boundary raises a quiet but decisive issue. Without light, there is no information. And without information, there is no control. In every branch of physics, observation depends on photons. From laboratory experiments to interplanetary navigation, light carries position, time, and state. NASA's Deep Space Network relies entirely on radio photons to track spacecraft millions or billions of kilometers away. ESA's Gaia mission maps stellar positions by counting and timing incoming photons with extraordinary precision. If light cannot pass, nothing else can substitute for it. Warp drive theory predicts precisely this kind of obstruction. In the Alcubierre geometry, the warp bubble is surrounded by regions of extreme space-time curvature. These regions act like horizons. Not event horizons formed by gravitational collapse, but geometric horizons formed by motion of spacetime itself. At these boundaries, the paths available to photons change dramatically. Calculations show that photons emitted from inside the bubble toward the front edge may never escape. The boundary moves away faster than the photons can approach it, even though locally the photons travel at the usual speed. From the outside, photons approaching the bubble can be deflected, trapped, or compressed, depending on the curvature profile. This behavior mirrors what is already understood near black holes. Near an event horizon, light emitted outward appears frozen to distant observers. ESA's observations of accretion disks and gravitational lensing confirm this effect repeatedly. Warp bubbles reproduce similar causal features without requiring a singularity. The consequence is immediate. If photons cannot cross the boundary symmetrically, neither can navigation signals, sensor data, or control commands. A warp bubble becomes a region that is partially or fully isolated from its surroundings. This isolation presents three distinct challenges. First, control. A spacecraft must adjust its trajectory, speed, and destination. In conventional flight, control signals propagate instantly within the vehicle, and external references are updated continuously through light. In a warp bubble, the geometry responsible for motion may be causally disconnected from the interior once established. Commands generated inside may not reach the front boundary where geometry must be shaped. Physicists analyzing warp metrics found that steering the bubble from within may be impossible. The region that determines direction lies ahead of the ship, beyond the reach of internal signals. This is not an engineering inconvenience. It is a causal limitation imposed by space-time structure. Second, observation. Navigation depends on seeing where you are relative to the environment. Star trackers, radar, LiDAR, and optical sensors all rely on photons entering the spacecraft. If incoming light is distorted or blocked by the warp boundary, the ship becomes blind. NASA's experience with deep space navigation shows how sensitive guidance is to even small signal delays. A warp bubble introduces distortions orders of magnitude larger. Incoming starlight could be redshifted, blue-shifted, or redirected unpredictably. Familiar reference frames would dissolve. Third, entry and exit. Even if a warp bubble could be generated externally, entering it safely poses severe challenges. As an object approaches the boundary, space-time curvature changes rapidly. Photons emitted by the object would experience extreme shifts. Mechanical stresses would arise not from acceleration, but from tidal gradients in geometry. ESA's studies of tidal forces near compact objects show how rapidly changing curvature can stretch and compress matter. Warp bubble boundaries may produce similar effects without warning. Crossing them smoothly would require precise matching of geometry on both sides. The issue of observation extends beyond navigation to detectability. Could a warp bubble be observed from afar? The answer appears to be yes, but not in comforting ways. Calculations predict strong lensing effects around the bubble. Light passing near it would be bent sharply. Background stars could appear distorted or multiplied, similar to gravitational lensing by galaxy clusters observed by JWST. Additionally, photon accumulation at the boundaries could lead to intense radiation signatures. As the bubble moves, trapped photons might be released intermittently, producing bursts detectable across large distances. These signatures would not resemble conventional propulsion. They would look like transient space-time disturbances. NASA's experience detecting gravitational waves is instructive here. LIGO did not observe objects moving through space, but changes in space-time itself. Warp bubbles would announce themselves similarly through geometry rather than exhaust. This detectability raises another concern. If warp bubbles can be observed, they can be interacted with. Incoming radiation, cosmic particles, and even interstellar dust would encounter the distorted geometry. Their behavior would be altered unpredictably. The cosmic microwave background provides a constant bath of low-energy photons throughout space, measured precisely by ESA's Planck mission. As discussed earlier, warp-induced curvature could blue-shift these photons dramatically at the front boundary. That radiation would not politely dissipate. It would accumulate. Control becomes even more fragile when these interactions are considered. The warp bubble would not exist in isolation. It would move through a universe filled with fields and particles, all responding to geometry. Another subtlety involves synchronization. Spacecraft systems depend on synchronized clocks. GPS, for example, works only because relativistic time dilation is corrected precisely. In a warp bubble, internal clocks may remain synchronized locally, but external synchronization could fail entirely. Without reliable photon exchange, time comparisons across the boundary become ambiguous. Events inside and outside cannot be ordered consistently. This undermines coordination with any external system. Carl Sagan emphasized the importance of communication in exploration. He often noted that exploration without communication is indistinguishable from isolation. Warp drive risks becoming the ultimate isolating technology, cutting itself off from the universe it traverses. Some have suggested controlling the bubble from outside. An external field generator could shape geometry ahead of the ship, allowing the interior to remain passive. This shifts the problem but does not remove it. The external controller must still interact causally with the bubble and its contents. Horizons do not disappear simply because the control source is relocated. Moreover, an externally controlled bubble raises safety concerns. If control is lost, the interior occupants may have no means of intervention. The geometry would evolve according to its own dynamics. Historical parallels are sobering. Early nuclear reactors taught engineers that systems governed by self-sustaining processes demand fail-safe mechanisms. Warp drive, governed by space-time dynamics, offers no obvious fail-safe once causal isolation occurs. Observation from the inside also becomes questionable. If light cannot leave, internal observers cannot send information out. If light cannot enter, they cannot receive updates. The ship becomes a closed system in a universe defined by open exchange. ESA's long-duration missions emphasize redundancy, communication, and continuous monitoring. Warp drive undermines all three. This does not render the concept meaningless. It clarifies its nature. Warp drive is not simply a faster engine. It is a space-time configuration with horizon-like properties. Interacting with it resembles interacting with black holes more than piloting a vehicle. Physicists take this analogy seriously. Black hole horizons limit observation, control, and communication. Warp horizons impose similar restrictions without the mass collapse. The universe has already shown us how such systems behave. They isolate, they trap information. They resist manipulation. This resistance may be the universe's way of enforcing consistency. Systems that could be controlled freely while violating distance constraints would destabilize causal order. NASA and ESA do not treat this as a failure of imagination. They treat it as a lesson encoded in space-time behavior. Warp drive, if it exists at all, would be less like a ship you fly and more like a space-time phenomenon you enter at great risk, with limited agency once inside. When all known constraints are taken seriously, the issue narrows to its most basic test. A warp drive may satisfy equations and respect carefully arranged conditions, yet still fail to exist as a stable feature of the universe. The remaining distinction is subtle but decisive: whether such a structure can persist as a physical system, or whether it survives only as a mathematical construction with no counterpart in nature. Part 10. Is warp drive a real physical possibility or a mathematical loophole? The most unsettling moment in the study of warp drive arrives when the equations stop arguing back, and nature is asked to answer directly. For nearly 3 decades, general relativity has allowed warp-like solutions without contradiction, yet every confirmed observation of the universe has remained stubbornly silent on their existence. Physics has faced this moment before. Mathematical elegance has often raced ahead of empirical reality, only to be corrected later by observation. Einstein's equations predicted gravitational waves in 1916, long before detectors existed. For nearly a century, those waves were treated as mathematical curiosities. In 2015, NASA-funded observatories finally heard them pass through Earth. In that case, nature eventually agreed with the equations. Warp drive now waits at a similar crossroads, but the comparison cuts both ways. For every prediction later confirmed, there are others that remain permanently unrealized. General relativity permits many exotic geometries. Closed time-like curves appear in certain rotating universes. Traversable wormholes appear under specific energy conditions. Entire universes can be written down that spin, collapse, or loop through time. None of these have been observed. JWST, ESA, and NASA surveys of the cosmos show a universe that is remarkably conservative in its large-scale behavior. Warp drive belongs to this family of permitted but unobserved solutions. The distinction matters. Physics does not declare something real simply because equations allow it. Equations describe what is consistent within a theory. Reality selects which of those consistencies actually occur. Over the course of this series, the pattern has become difficult to ignore. Warp drive respects the local speed of light, but challenges global causality. It avoids traditional acceleration, but demands extreme space-time curvature. It obeys Einstein's equations, but violates the energy conditions that keep those equations physically grounded. It can be written down cleanly, yet resists control, observation, and stability. Each problem alone might be solvable. Together, they form a coherent resistance. NASA and ESA do not dismiss warp drive as fantasy. They treat it as a diagnostic tool. By asking whether warp drive can exist, physicists probe the limits of space-time itself. The question becomes less about transportation and more about structure. One lesson emerges clearly. Space-time is flexible, but not freely moldable. It stretches under cosmic expansion. It ripples under violent mergers. It bends around mass and energy. Yet it appears to resist deliberate reshaping that preserves local calm while imposing global distortion. The universe does not behave like a passive medium awaiting engineering. Observations reinforce this. JWST reveals early galaxies forming faster than expected, yet still within gravitational constraints. Gravitational waves stretch spacetime, but only briefly. Black holes warp geometry intensely, but at the cost of horizons and isolation. Every extreme phenomenon carries a price that preserves consistency. Warp drive attempts to collect the benefits without paying the costs. Energy accounting offers another anchor. Conservation laws have survived every experimental test to date. They adapt to relativity and quantum theory, but they do not vanish. Warp drive's reliance on exotic energy strains this resilience. Quantum field theory permits small, fleeting violations, but forbids accumulation and control. The universe appears willing to tolerate exceptions only when they cannot be exploited. Causality sharpens the boundary further. The order of events has remained intact across billions of years. Light from the early universe arrives when expected. Stellar evolution follows consistent sequences. Even quantum entanglement préserve causal signaling limits. Warp drive presses against this order without offering a stable resolution. Stephen Hawking's intuition about chronology protection gains weight here. The universe behaves as if it actively prevents configurations that would undermine temporal order. Warp drive flirts with that boundary. Does this mean warp drive is impossible? Physics rarely answers with absolutes. It means something more precise. Within our current understanding, warp drive occupies a region where mathematics outpaces evidence. This gap does not invalidate the mathematics. It challenges our assumptions about applicability. Carl Sagan often reminded us that science advances by balancing openness with restraint. It is a far better thing to grasp the universe as it really is than to persist in delusion, however satisfying and reassuring. Warp drive invites us to test that balance. If new physics exists beyond general relativity and quantum field theory, warp drive may find a footing there. A deeper theory of spacetime could revise energy conditions or causal structure in controlled ways. History allows that possibility. But until such physics is revealed by observation, warp drive remains what it currently is, a mathematically consistent solution, lacking empirical support and burdened by compounding constraints. That conclusion is not a failure. It is an achievement. It tells us that the universe is not easily tricked by clever geometry. It guards its structure with multiple, overlapping principles. Light, energy, causality, and quantum behavior all participate in that defense. Warp drive has taught us something valuable even without existing. It has shown us where spacetime bends, where it resists, and where our theories still leave unanswered questions. And that may be its lasting contribution. As this journey through equations, observations, and limits comes to rest, it is worth holding on to a simple truth. The universe is vast, subtle, and consistent. Its rules are not barriers placed in our way, but reflections of how deeply connected space, time, and matter truly are. Thank you for spending this time exploring these ideas together. If listening has brought even a small sense of calm curiosity, I'm grateful you were here. Wherever you are, may the rest of your night be steady, clear, and untroubled, as the universe continues its patient work around us. Wishing you a restful night and an easy sleep ahead.